In order to describe lasers, we'll start with the light that they make, and then we'll talk about where that light comes from. So the light from a laser is coherent. That means over a long distance, phase coherence is maintained. I can trace out a single sine wave from beginning to end of a laser beam over at least a distance called the coherence length of the laser. And the time it takes light to travel the coherence length is the coherence time. The light that comes out of a laser is not necessarily a beam, but optics outside of the laser are used to collimate it into a beam. We'll talk a little bit about the issue of the light coming from a laser not being perfectly monochromatic. It is a very narrow line that is generated from this process of stimulated emission, but it's not as narrow as is usually needed, and so again, external optics are used along with a resonant cavity to narrow that up even more. Light's described by Planck's radiation law, which you learn about when you study thermostatistics. I of omega is the irradiance of light. That means that's the power per unit area per frequency coming out of a laser. And it's given by this expression which contains in the square brackets something that you might recognize as the Bose-Einstein distribution, because light is composed of photons and photons are bosons. The spectral irradiance is also related to the energy density, because what is in a light beam is electromagnetic energy traveling at the speed of light at c, and the spectral irradiance is given by the energy density in the electromagnetic wave times the speed of light over 4. And that is all worked out in thermostatistics textbooks such as Blundell and Blundell, referenced below. Since I of omega is the irradiance per unit frequency, where omega is 2 pi frequency, this expression needs to be integrated over all of frequency to find out how much intensity, that is power per unit area, is coming out of the laser. And so I, without the omega dependence, is in fact the total emitted power per unit area from the laser, and that's the total irradiance. If this expression for spectral irradiance is rearranged, we have a useful expression then for the electromagnetic energy density in a laser beam, which we will use later, so you want to write this down. That's why it's in a red box. Electromagnetic energy density goes as the frequency of the light cubed times the Bose-Einstein distribution. That's a brief description of laser light. Where does it come from? That begins with a description of how radiation and matter interact. And there are 3 ways. First is spontaneous emission. If you have a two-state system, now this could be an atom with a ground state E1 and an excited state E2. This could be a semiconductor with a valence band edge E1 and a conduction band edge E2. But it's in its simplest form a two-state system. If you excite a electron from the ground state E1 to the excited state E2, it will stay there for some lifetime, and then it will decay back down to the ground state, emitting a photon. And that's spontaneous emission, spontaneous because it happens without any external motivation. There's just a lifetime of that excited state, and then it goes to the ground state. The energy of the photon, E sub gamma, is the difference in energy levels, E2 and E1. If a photon were to happen upon this system, then it can be absorbed, and an electron that was in the ground state can be kicked up to the excited state. Now that happens when the photon has an energy that equals that energy difference, and that's why it's resonant absorption, because the energy that comes into that photon needs to be the same as that energy that the electron requires in order to get up to the excited state. With an electron in the excited state, it can go back home through spontaneous emission, but there's another more remarkable method that involves perturbations. If an electron is in that excited state and a photon whose energy equals the energy difference between E1 and E2 encounters this system, it could tickle that electron that's in the excited state, causing it to jump back down to the ground state. And because all it did was tickle that electron, that incident photon does not get absorbed. So the incident photon continues on by the atom, but it brings a new photon with it. So it's one photon in, two photons out. And that's stimulated emission, which is a key process for the operation of a laser. These two photons coming out are copies of each other. They will not only be in phase and have the same polarization, but they'll have the identical wavelength as well. So let's focus then on stimulated emission. If I have an ensemble of two-state systems, so it could be a large collection of atoms, or it could be a lot of electrons in the conduction band of a semiconductor. Some of the electrons are in the ground state of energy E1, and some are in the excited state of energy E2. I have a certain number in each. The number of electrons in the ground state we'll call N1, and we'll call the number of electrons in the excited state N2. We'll have photons, plural, of energy E2 minus E1 incident on this ensemble of states. When one of these photons strikes one of the systems, it can tickle that electron in the excited state, and out comes two photons, both of energy E2 minus E1. And the goal then is to have a lot of that going on. We have to analyze this statistically. The electrons are fermions, therefore they're going to obey Fermi-Dirac statistics, whereas the photon obeys Bose-Einstein statistics. The nice thing about fermions is that their population can be described by what's called the Fermi function, as long as you're at a reasonably high temperature. So the number of electrons up in the excited state is proportional to e to the minus energy of that excited state over kT, and the number of electrons in the ground state is proportional to e to the minus energy of the ground state over kT. So the fraction of electrons that are in the excited state is N2 divided by the total number of electrons, which is N1 plus N2. Replace those N's with the appropriate Fermi function, e to the minus E2 over kT for N2 with e to the minus E1 over kT for N1. Multiply top and bottom, I didn't show it, by e to the plus E2 over kT, and you can rewrite this as 1 over 1 plus e to the delta E over kT. I suggest you stop for a minute and just make sure you follow the algebra from the second to the third statement here. I then want to point out an important factor of laser light, and that is that the frequency is kind of high. It's light. And so h bar omega, delta E in other words, the energy of the emitted photon is large. Typical values are a few electron volts. kT, on the other hand, is Boltzmann's constant K times temperature T in Kelvin. The product at room temperature of Boltzmann's constant and 300 Kelvin is 0.026 electron volts. So kT is a very small number compared to delta E, meaning that this exponential is much larger than 1. So I'm going to ignore this 1 plus, and that's a very important feature in statistical mechanics, that you can usually do that, especially at room temperature, and it really simplifies a lot of expressions. So N2 I'll write as N1 times e to the minus h bar omega over kT. So again, make sure you can follow through this algebra. Ignore the 1 in the denominator and replace delta E with h bar omega, and make sure you agree that N2 is N1 times e to the minus h bar omega over kT. If you put some numbers in, 2 for h bar omega, 0.026 for kT, you'll realize that N2 is much, much less than N1. You have to get extremely hot for N2 to become significant. That is, temperature T needs to be very high so that kT can be large and you don't have N2 being a very, very small number. The problem is that even at infinite temperature, N2 will never exceed N1. So if you want to have a lot of electrons in the excited state, which is necessary to have a lot of stimulated emission, we need some other way than heating up the medium to get electrons into the excited state. Population inversion is the situation where you have more electrons in the excited state than you have in the ground state. And that has to be accomplished some other way than temperature. And that way is essentially inelastic collisions. Collisions with electrons to move them into the excited state and give them energy. Collision with an atom, collision with something that can deliver an impulse and raise it up. Once we have more electrons in the excited state, E2, than we have in the ground state, you say that population inversion has been achieved. Now there's a balance between the rate that electrons are being excited from E1 to E2, the rate that electrons are spontaneously dropping from E2 back to E1, and the rate that stimulated emission is occurring. That's thermal equilibrium. I'll put it this way. The rate that electrons are excited up to E2 is the rate that electrons are decaying back to E1. And they're decaying back to E1 by two mechanisms. I'll just describe them as desired and undesired. What we want to have is stimulated emission so that there's amplification of the photons, more come out than go in, and they're in phase with each other. Any other mechanism of decay is undesired. The other method is spontaneous emission. So we want to have most electrons decaying from E2 down to E1 via stimulated emission, not spontaneous emission. So we need to find a way to control that. And one way to make sure that happens is to achieve population inversion. Let's look at these three rates individually. First, resonant absorption. So the more electrons I have at level E1, the more electrons are available to absorb a photon and excite to the level E2. So the resonant absorption rate is certainly going to be proportional to how many electrons there are down in the lower level, times the rate that each atom can absorb those photons. Now that's going to depend on how much energy is available. That is, how many photons are available to be absorbed. And so we'll call that the energy density, which you can think of as the number of photons per volume for now. It's actually the energy per volume. If you take the absorption rate per atom per energy density, that is, you need a lot of energy in order to have absorption, and multiply by that energy density, you will have the resonant absorption rate. N1 is the level 1 population. Rho is the energy density. We'll just call the absorption rate per atom per energy density B for now. The spontaneous emission rate is a little simpler because the rate that you have spontaneous emission will not depend on the electromagnetic field that is present, because the function of the electromagnetic field is to give the energy to the atom to excite the electrons. That doesn't have anything to do with emission. So you can have spontaneous emission just by having electrons in the upper level. So you take the level 2 population and just multiply it by the known decay rate per atom. You have the spontaneous emission rate. And 2 is the number of two-level systems that are excited. And we'll just call the decay rate per atom for now A. Then there's stimulated emission. Now that does depend on the ambient electromagnetic field, because in order to have stimulated emission, you need to deliver a photon to the atom. It certainly depends on the number of states that are excited, and it will depend on the energy density, because that's essentially the number of photons that are available, and then it will depend on the stimulated emission rate per atom per energy density. Now that is also equal to B. Think of this middle term, stimulated emission rate per atom per energy density, and up in the top equation, absorption rate per atom per energy density. Those are probabilities. Think of them as the probability that if a photon hits an atom that's in the ground state, this is the probability that it will be absorbed. If a photon hits an atom in the excited state, this is the probability that it will be re-emitted. Those are essentially the same probabilities. You may have more atoms in the excited state, or you may have more atoms in the ground state, but the probability is specific to just one system, so one atom. So it's the same probability regardless of which way you're going to go with that photon. If your system can excite with the photon, or if your system can decay with that photon, it's the same probability. Write the expression this way: resonant absorption rate is spontaneous emission rate plus stimulated emission rate. This A and B do have names. B is called the Einstein B coefficient, so just remember it's the absorption rate per atom per energy density. Rho is the ambient electromagnetic energy density, often called the pumping field energy density, because it's the field that both sends the electrons up into the excited state and then stimulates the emission of a second electron. A is called the Einstein A coefficient, and it's just the decay rate per atom. It's the number of decays that one atom is capable of undergoing per unit time. Well, it can only undergo one decay, but the real question is how much time passes before that decay happens. So 1 divided by A is how long it takes an atom to decay on average. So A is 1 divided by the lifetime of the excited state. That's a very simple meaning for the Einstein A coefficient. Write this expression down because now we're going to use it. First, let's rearrange the expression. I want to get the energy density all by itself on one side, so just a little algebra here. Rearrange it like this and then solve it for rho. So you have this expression for the electromagnetic energy density on one side, even though it's by no means a dependent variable, but it will put it on one side and the Einstein A and B coefficients and the populations on the other side. Going back to our statistical mechanical argument that the number of states that are excited is equal to the number of ground states times e to the minus h bar omega over kt, we make that replacement. Put that in for N2, and that way you eliminate N2, and you just have N1, but you can cancel out because it's everywhere. And then I will do what I often do and multiply this expression by 1. And today's choice of the number 1 is the ratio of e to the h bar omega over kt over e to the h bar omega over kt. That allows me to further simplify the argument to this expression. Keeping a over b outside some parentheses, inside the parentheses we have this expression. Equate this to the Planck radiation law from before in order to eliminate the exponential term in the brackets, and you have an expression now for A over B. Using the statement that angular frequency omega is 2 pi c over lambda, it's better to be talking about wavelength than angular frequency in the end. That's a nice simplification. And you have that A over B is 8 pi h bar over lambda cubed. A very simple relationship then between the Einstein A and Einstein B coefficients. When wavelength is 0.014 nanometers, that ratio equals 1. And why is it important that A over B is 1 at that wavelength? Because what you really want to see is that ratio A over B being as small as possible, because A is your spontaneous emission rate, and you don't want spontaneous emission. You want stimulated emission. So you want A to be small and B to be big. That's achieved by population inversion. When you have population inversion, A over B will be small. But how do we get a small A over B? For starters, you need a long wavelength. Long wavelength lasers are more efficient. Infrared and visible are pretty efficient. But when you get to these really short wavelengths, then it becomes much more difficult to have an efficient laser. I've seen some fairly efficient diode lasers in the near infrared. When you start to get to like ultraviolet, and yeah, that's a much more challenging proposition. So let's go back to A. It's 1 over the lifetime of the excited state. We need our excited states to be very long-lived in order to have a good laser. For example, the helium-neon laser takes advantage of the excited PHYS state of neon, which has a 100 nanosecond lifetime. That turns out to be long enough to make, well, helium-neon lasers. So we'll take a close look at the HeNe laser shortly. We need to then talk about population inversion. Going back to our ratio of states that are excited divided by the total number of states, you can put in a typical energy. So for example, the helium-neon laser, we have this 1.96 electron volt delta energy. Put in your 0.026 eV for room temperature, and you find that only 10 to the minus 33 states are excited. That's the ratio of excited states. Well, what about when the temperature gets high? Well, even if the temperature goes to infinity, this only goes to 1/2. That's a classic two-state problem where you can never have more than half of your states excited due to thermal excitation. So population inversion won't happen just from temperature. It won't happen on its own. You have to design a system that makes it happen. So we have to input energy, and it can be input through collisions. In a gas laser, collisions with other atoms. Like in a helium-neon laser, helium atoms collide with neon atoms to get the neon atoms excited. In the case of a diode laser, you have current injection, so impact ionization from injected current. And you want to have more N2 than N1, because when that's the case, stimulated emission will dominate the system, as opposed to having more systems in the ground state, in which case you have a lot of resonant absorption going on, and all those photons that get generated by stimulated emission end up being lost by resonant absorption, and you can't get an avalanche. In order to get the avalanche, and in order to shape the spectrum of the beam, we need to place the lasing medium, like the gas or the semiconductor, in a resonator. The problem that we have is that whether it's a gas laser or a diode laser, the line widths are broad. That is, you expect only one wavelength to be coming out when you have stimulated emission, but in fact, due to Doppler broadening, you have a width of line widths coming out. In the case of the helium-neon gas laser, it's about 1.5 gigahertz wide, 0.02 angstroms wide. Resonant cavity is employed to narrow that up to something on the order of, there you go, 0.005 angstroms, but I say for example because that's a design parameter, and it can vary a lot from design to design and application to application. The diode lasers are broader band. You might have a 2 nanometer broadened line width. If you look up specifications on laser diodes, you'll find that manufacturer specs usually indicate about a 2 nanometer to 5 nanometer broadened line width. And that has to be narrowed up too, and it typically can be narrowed up to less than 1/10 of an angstrom. You put this active medium between two reflecting surfaces. They may be curved in the case of a gas laser, or they may not be curved in the case of, say, the semiconductor die. You get a resonance between there. You have this distance of L, the length of the active medium, and so you have resonant conditions. It's a Fabry-Perot resonator. The free spectral range is the frequency distance between those resonances, and if you have this broadened spectrum, given this broad red line, and it's placed inside this resonator, then you should only expect to see emissions at these particular frequencies. So then you have the ability then to select out which frequencies are going to be emitted. Outside of these resonant frequencies, there simply won't be photons available to generate stimulated emission. And this allows then the narrowing of the spectrum that comes out pretty significantly. Let's look specifically at the helium-neon gas laser. So there are 2 atoms present. Most of them are helium, and then somewhere around 10% of the atoms present are neon. Helium's first excited state, that is, an electron is moved into the 2s subshell, is 20.6 electron volts above the ground state. The way you get an electron up into the excited state is by collision with an electron beam. The gas is contained in a cavity, which also serves as the resonator, and is biased in order to accelerate ambient electrons from one plate to the other. And as those ambient electrons accelerate through the gas, they strike the helium atoms and excite some of them up to the 2s subshell, which is 20.6 electron volts up there. That's metastable, meaning there's no way for those excited electrons to get back down to the ground state, because you aren't allowed to have a transition from an s subshell to another s subshell. So we have all these helium atoms then floating around in the excited state. Now it just so happens that neon has a particular state that is 20.6 electron volts above its ground state. So if all of these neon atoms in the gas are in the ground state, neon atom collides with a helium atom, the helium atom can give up its energy. This 2s electron goes back down to the ground state, and it excites this ground state 2p6 electron in the neon up to the 2p5s state. 2p is the subshell that is filled when neon is in the ground state. So now we have an excited neon with an electron way up here in this subshell, and that electron will stay up there for a little while. That state has a lifetime of 100 nanoseconds, so it's eventually going to decay on its own, but if along comes a photon, it can expedite the decay of that electron into the 3p subshell and emit a photon of 1.96 electron volts. and that's the stimulated emission. In comes one photon, and out goes two photons of energy 1.96 eV, which happens to be 632.6 nanometers. In the case of a helium-neon gas laser, we'll say that we have population inversion when there are more 5s subshells that contain an electron than there are 3p subshells. And that's a pretty easy condition to meet, because normally why would there be any electrons in the 3p subshell? I should also point out that there are a lot of states in the neon atom. If a photon were emitted from the 5s subshell as an electron decays into the 4p subshell, a 3.4 micron photon will be emitted. And that's the basis for the helium-neon infrared laser at 3.4 microns. So the basic steps to getting a helium-neon laser to produce coherent beam is first to excite the helium atoms with an electron beam, and then use those helium atoms to excite the neon atoms into that specific state of 2p5 5s. After about 100 nanoseconds, there will be spontaneous emission, and at first that's good because it sends a whole bunch of 1.96 eV photons into the medium. Those photons then strike other neon atoms that are still excited and produce stimulated emission, and you get your avalanche from that. You might ask, why not just hit the neon atoms with the electron beam? Well, we do, but why not just depend on that? And why is the helium necessary? Because when you send that electron beam into just pure neon, electrons will be excited into all of the states, and not specifically that one. So the stimulated emission of 1.96 electron volts will be very dim, and you have a very populated spectrum of the other wavelengths. So that's the reason for using two components in the gas. So that's the helium-neon laser. I do have a few other videos you can watch on semiconductor diode lasers as well.